Hello, everyone, and welcome to ACSESS 2021. My name is Chris Lehnig, and I will be sharing with you our research on estimating the impact alternative spring break schedules will have on reducing total COVID-19 incidents on college campuses. So a little background, last year, a lot of evidence emerged that college students returning for spring break 2020 contributed to a rise in local COVID-19 incidents in their hometowns. As a result, many US universities implemented alternative spring break schedules for the 2021 spring semester. As far as we know, there hasn't been any research comparing the impact different schedules will have on COVID-19 incidents, which is what we attempt to do in this study. So virus transmission is simulated using this compartmental model. The size of our simulated student population is 5,000, and the way this model works is that students are placed into one of these mutually exclusive compartments. Transitions between compartments are based on contacts and biological parameters related to the virus. During simulations, students that travel during a break actually leave this model and enter a similar model. The main difference is that in the traveling student population, the numbers of infections is predetermined as based on several factors, which we'll discuss shortly. After a break is over, traveling students are added back to this model and the simulation continues to run. To determine what alternative schedules to model, we sample 25 universities and visualize their schedules in the figure on the left. Each tick on the y-axis represents one university. They are colored by the number of shorter breaks that replaced their spring break. So we had 1, 2, 3, and 4 break schedules. Each bar in the plot spans the start to end date of each break period. So we decided to model these 4 break schedules. Within each schedule, the start date of each break period in our model is based on the average start date weighted by each break duration. So for example, in our 1 break model, we looked at the start dates of these 9 universities and took the average weighted by the duration of each break. To calibrate our base model, we surveyed COVID-19 dashboards of 8 universities and noticed the same pattern observed here at SDSU. That is a large surge in cases in the first couple weeks of the semester, followed by small counts afterwards. Parameters in our base model were fit to mimic this trend. This last figure shows an example simulation. As you can see, there's an initial surge in cases during the start of the semester, followed by a steady decline. The horizontal bars at the bottom down here visualize the start date and duration of each break period within our 4 break schedules. There's more to the simulation we can discuss, but first we need to go over the dynamics related to traveling students. Determining how many students will travel during a break and how many of them will return infected is complicated, so we decided to model a range of possible scenarios. The number of students that decided to travel is represented as a function of break duration. Using cell phone locations from SafeGraph mobility data as a proxy for student movement, we noted that the number of students traveling during this past Thanksgiving, which was a 5-day break, is roughly 3 times the number during Labor Day weekend, which is a 3-day break. This relationship zips in these 25 curves. That is, the value of 5 days is approximately 3 times the value of 3 days. These are scaled and shifted sigmoid functions, and they were selected to cover a range of probable student movement behaviors. To determine how many students are infected while traveling, we ran 105,000 Monte Carlo simulations. So inside the Monte Carlo simulation, we accounted for the mean daily contact rates of the traveling students relative to their base model. So we looked at 1 times up to 6 times the number of contacts compared to when they were on campus. We looked at 5 different prevalence rates values. Those are the prevalence rates at the destination location, which determine the likelihood of coming into contact with an infectious individual. Transmission actually happened based on the probability of transmission that was derived from our base model. And we looked at these values for break durations 3 to 9. So given an assumed daily contact rate, a prevalence rate, and length of a vacation, our model outputted the percent of the traveling students infected. So here are our results. Since we considered a wide range of scenarios, we ended up running 3,000 simulations. The top row shows total COVID cases during the entire semester in the 1 break schedule. The remaining row shows the percent reduction of these cases in the other schedules. The y-axis in each panel indicates which student movement behavior curve was used in the simulation. The x-axis indicates the mean number of daily contact used to determine the percent of traveling students infected. Looking at the first column, if the mean destination prevalence is 2%, then in most scenarios, the alternative schedules will have little impact. It's only when we see higher student movement and more contact while traveling that we see a 10 to 6% reduction in cases. In the next columns, we see that the 3 and 4 break schedules show about twice the percent reduction compared to the 2 break schedule. As prevalence increases to 6, 8, and 10%, we start seeing significant reductions in total cases by implementing alternative schedules, up to 40% in our most extreme scenarios. We hope that universities can use the results in this figure to determine the most likely possible outcome given the behavior of their student body and the projected prevalence of COVID-19 at the time. Thank you very much and have a good day.